this, and it's the proximal convoluted tubule. The apices of this are going to be impermeable to bicarbonate. Bicarbonate has to get converted into something else so it can be reabsorbed and buffer blood. This is our old friend, the bicarbonate buffer equation. So here you have bicarbonate, here you have the hydrogen ion, and we're going to convert them, remember we said, into water and carbon dioxide. The water is going to be excreted or reabsorbed depending on what your need is, and the apices of the proximal convoluted tubules are going to be permeable to carbon dioxide, so you can get that in your tubules. So once the epithelial cells of the proximal convoluted tubule, carbon dioxide is converted back into bicarbonate, so you're going to have the carbon dioxide get converted into bicarbonate and hydrogen ions. Bicarbonate is reabsorbed into blood in exchange for the chloride, and then remember that's going to equal the chloride shift, or bicarbonate is going to be antiported with sodium secretion. Hydrogen then is going to be secreted back into the lumen of the proximal convoluted tubule and is antiported with sodium reabsorption or by hydrogen pumps. So this is the business end of what the kidney does, which is exactly what the red blood cell did. So here we are on the lumen side. This is the filtrate from the glomerulus. Fluid's coming down here. You have the capability, if you need to get rid of hydrogen ions. So here, if you get rid of hydrogen ions, you're going to have sodium ions come in there. Remember, this is an antiporter. So then you're going to have to get rid of that sodium, and remember, to get sodium out of here, you've got to kick in a little ATP to do this. So if you get rid of the hydrogen ions, you're going to have carbon dioxide come in here. Carbon dioxide, remember it said that this is permeable to carbon dioxide. Carbon dioxide is going to come in here, encounter water that you have inside this cell. That water, most of this water, is the metabolic water that you're making from the electron transport system. So feature this. So you get your water and your carbon dioxide in the presence of your old friend, carbonic anhydrase, into carbonic acid. Carbonic acid then will dissociate. You can still get rid of those hydrogen ions and get more sodium in there, and then you get your bicarbonate out of here into blood, back into blood, and you don't have to pay for this because you have a special shuttle for that. So now all you have to do to keep this going is drive this ATP shuttle so you can constantly get rid of these hydrogen ions. Does that make sense? It should.
So when we have this essay question, you're going to ask us to describe the regulation of kidney. Is there a second part to it?
Yeah, so this is blood pH. How do you regulate blood pH? How do you regulate ionic composition would be the first one. That's all the ions and how they move across, either paracellularly or transcellularly. This is the pH effect. So when would you want to get rid of these hydrogen ions? When your blood pH is high or low?
Low.
If you have a low blood pH, your blood's going to be acidic. So what you're trying to do is increase your blood pH. That's why you're trying to get rid of it. Let's take a look at this. Hydrogen ion, bicarbonate reabsorption. So here you are, here's the lumen. You have this ingoing equation that we just talked about up here where you have the hydrogen ion and you have sodium antiported. But now what you can get is you have bicarbonate out in that filtrate. And if you want to get that back in here, you have to combine that with the hydrogen ions that are out here in the lumen. Turns out on these microvilli, you have the enzyme carbonic anhydrase to form bicarbonate, which then will dissociate into water that will become part of that urine. And then you get that carbon dioxide because this is freely permeable. When you get the carbon dioxide inside the cell, you're going to put it back through this equation, combine it with the metabolic water, carbonic acid, you get dissociated that into the hydrogen ion, and now you get that carbon dioxide that you had in here reconverted into bicarbonate so you can get that back into blood. So this is showing you how you can secrete hydrogen ions with sodium reabsorption, and here you can reabsorb bicarbonate ions in this situation. Here, what you're getting is if you get the CO2 back, this is getting your blood, the ability if you're a little basic. So here's your little control. This is a negative feedback mechanism. You have, it's a homeostatic mechanism, so every time your blood pH, say, increases in hydrogen ion concentration, that means your blood is getting more acidic. Then you have chemoreceptors in the aortic sinus and the carotid sinus, and then you have in the medulla, you have these chemoreceptors that are sensing that. That's going to cause you to change the way you breathe. Remember in our respiratory discussion when we talked about respiratory acidosis and alkalosis? You remember what the compensation mechanisms were for those? It was changes in breathing. Changes in breathing here, so the diaphragm is going to contract more forcefully so you can get more CO2 exhaled. As less bicarbonate forms and fewer hydrogens are present, blood pH is going to increase, hydrogen ion concentration decreases, so that's going to continue to work itself along, and you will alter your breathing until you restore a normal blood pH. But just like we saw it in respiratory alkalosis, in metabolic acidosis or alkalosis, you haven't solved what the problem is. All you've got is your pH back to normal. You're still going to have problems with these acids and bases, and you have to get that resolved. So here's your metabolic acidosis, alkalosis. It's decreased